Okay, here we go. So chemical potential energy is our focus for today, and it will also bleed a little bit into the thermal side of things as well. So chemical potential energy, as we mentioned last time, is the energy that happens as chemical bonds are changing. So first I have to start you with a question here. It says, what energy types are present in the working microwave? What energy is being put in and what energy is being put out? So talk to your table buddy, and let's just once again kind of recap what we did last time. And then we'll go next. Turn to your table buddy, talk about the different types of energy. Ready, go.
Electromagnet. Oh, what is it? What? So I think it's
I don't know if we care. At least not. One day I'll just show my I am thinking about casting off aluminum, so that'll be fun. Just show off.
Crazy.
We got our schedule this week, and it's like
By raise of hand, would somebody be willing to share with us what they identified here? What's the energy starting as? Where's it going? Go ahead, Caleb.
electrical to electromagnetic to thermal.
Good. So he said starts out as electrical because it gets the energy from being plugged in, turns into electromagnetic, that's the microwaves, and then also we get thermal as well. Anyone else have anything different or something else you would add to it maybe? Yeah, Kate?
Sonic, because it makes like sounds.
Yeah, I'd say definitely some sonic as well, right? Like some of it. Now keep in mind, once again, there's a difference between energy that's useful and then energy that just, you get to say is waste or just dissipates, right? In terms of the sound is not useful energy, right? Like that doesn't help in the process of the food at all. But obviously it's what some of the energy gets transferred into, and that's how it kind of always goes, is there's always in the end some energy that gets wasted. And that's kind of the goal a lot of times of when people are building things, is how can I maximize and try to prevent the waste of energy. By the way, if you said similar things, I'll say give or take the sound one, you can have a smiley face as well. Caleb, you can have 2 for sharing this out loud.
Yeah.
Okay. So as a reaction happens, what we need to remind ourselves of is they involve the breaking of chemical bonds and then the formation of new bonds. So bonds break, new bonds form. Okay? The number of atoms before and after we know must stay the same. That's why we balance chemical equations. Okay? But things happen as they get rearranged. Thank you. Right, so here's kind of a picture to show that process of in making of water. You have H bonded to H bonded to H, O double bonded to O. But in order for it to become water, these all have to break and those new bonds get formed. Okay? That's the one. Okay. So in order for a reaction to happen, a few things have to be in place. Okay? Key thing is they have to have enough energy in the collisions. And we'll actually have a whole unit about collisions. For now, just recognize that molecules have to collide and they have to have enough energy. If they don't have enough energy, it's just bumper cars and they bounce off each other. But if there's enough energy, then there's the possibility to break the bonds and form the bonds. Okay? All right, I want everyone to take your hands with me because often students get this mixed up. So we're going to do just a very simple but tangible thing with our hands to help us remember. So everyone, I want to take your hands and I want you to link them together like you're a chemical bond. Okay, everyone, make a bond with your hands. I guess we could be cute and we could make bonds with our neighbors. We'll make it with ourselves for now. Okay, all right, so bond here. In order to break this, energy has to go in. Okay, bonds, if I'm gonna break this, energy has to go in to break it. Okay, students often mix it up and they think the opposite. And they think bonds are like a popper, you know, where you pop it and boom, it comes out. That's opposite, right? Energy doesn't come out when the bond breaks. You have to put energy in to break it. On the reverse side, when a new bond is formed, so I want you to reach across the table and make a bond with your new friend, just real quick. Okay? So you do a three-way bond, whatever. Okay? So do you feel the energy? Right? So energy gets released when a new bond is formed. Okay, you can come down. Okay, so if I'm doing this and I want to break it, what has to happen? Energy has to go in, right? And to make a new relationship, or when a new relationship forms, what happens? Energy comes out. Okay, so coming together, energy out, breaking apart, energy in. Okay, so as we look at this, in all chemical reactions, there's always going to be both. Okay, so as we talk about this idea of collisions, key thing is once again, even if they collide and have enough energy, it still doesn't always mean it's going to work out. They have to collide with enough energy, and they also have to collide in the right way, because there's certain places they want to bond, and if they don't bond in that certain place, then once again, it's just bumper cars. And once again, we'll have a whole unit where actually we'll talk more about this. Okay, key thing once again I want you to recognize here is that you need enough kinetic energy, which is movement, to break the bonds. Otherwise, they'll just stay linked together. Okay, everybody okay there? Our first classification, as we talk about this idea of a chemical potential energy, is we have what are known as exothermic and endothermic reactions. Okay? With our exothermic, oh, this is out of order. Is that out of order for you? Like we just, because this is this, and we just did what was below it. Am I right? Okay, sorry about that. That's confusing. Okay, let's get this in, and then we'll talk about exo and endo. So activation energy is the energy it takes for the reaction to occur. It's like the minimum payment it's needed to make it go. Once you have the minimum payment, then it can continue on until it's done. Once again, the best way I found in science to define a two-word something, so like this is like a two-word, right, activation energy, is to read it backwards. It's the energy to activate. Right, so if you're like, what does that mean? I found that holds true with a lot of words actually in science. If you're like, I don't know what this means, try looking at it backwards and sometimes it defines itself for you. Which I know is like against laws of English to use the word in its own definition, but I don't teach English for a reason. So, okay, everybody okay now? Okay, now let's talk about endothermic and exothermic. Okay? Oh, maybe not. Was there one more I missed? Sorry, I am like all over the place. Do we have all three blanks there? Okay, let's go to endo and exo, because that's what our lab's got today. So endothermic reactions are reactions that release or give off energy. Okay, so they are a reaction that after the reaction occurs, it gives off energy in the form of heat. After you fill these in, I want you to take your, pick a highlighter of your choice, and just to help you out here, I want you to highlight EX in exothermic. The thing with these two words is obviously there's just two classifications and they're opposite of each other. The easiest way to not mix them up is to recognize this prefix of EX in like the word exit. And so the heat is exiting the reaction. Okay, so that we can kind of, and we'll notice it in the other ones. are going to have less energy than the reactants. So the second thing I want you to highlight here is you highlight the EX, is highlight this product line on the graph. Notice how it's lower than the reactant line. That means that this reaction is exothermic. Our goal today is that you can identify whether something is endo or exothermic, either from given data or from a lab. Okay, so that's kind of the goal. By the end of the day, is you can see something like, oh, that's an exothermic process, or that's an endothermic process. The other thing I want you to identify on our graph here is the uphill and the downhill. Okay? All right, when we were making our little bonds here, if I have a bond and I want it to break, will it just break on its own, or does it take energy? It takes energy. So everyone, write with your pencil that anytime you're climbing up a hill, meaning energy's going in, this means bonds breaking. Okay, so the uphill always implies the energy it takes to break the bonds. What happens when you make a new friend?
Bonds form.
And the energy does what, Taylor?
Goes down.
Good, or comes out, right?
Comes
so
out.
energy comes out
Gone.
when a new bond is formed. So the downhill is bonds forming. Yeah,
What
please.
does the first one say?
Bonds breaking. Yep, so uphill is bonds breaking. I'm paying money to break the bonds, aka the money's the energy. Then the reaction starts paying me back as the bonds form. And if it's overall exothermic, which one am I getting more of? More out or more in? More out, right? So keep in mind there's always both. Bonds always break and bonds always form, but the overall classification is based on which one do you have more of. Do you have more energy coming out, or did more energy go in? Okay? All right, questions so far? Okay, let's look at endothermic, right, which is obviously everything's the opposite. Okay, so endothermic, the reaction is absorbing or taking the energy in. The products now have more energy than the reactants. And we can think of energy as like a reactant, meaning you need energy for the reaction to even happen. Because it's part of making it go. Okay, so once you get those blanks filled in, grab your highlighter again, and I want you to highlight the opposite here. So the prefix is the EN, right? Think of enter, right? That prefix, EN, right? The energy's going into the system. And then notice this time that the products now are higher up than the reactants. The hills are still the same. Going up is still bond breaking. Going down is still bond forming. But if it's endothermic, which one is giving me, what's there more of? Yeah, right? Like it's costing more to break the bonds than what I get back. Right? More's going into the system than what's coming out of the system. Okay, any questions for now on the difference between endothermic and exothermic? Okay, final piece to this before we go into our lab today is with endo and exothermic, obviously they're opposite of each other, which makes it sometimes more confusing when then it's just two options because it's easy to get it backwards. The thing you have to be cautious with when you're thinking endo and exo is what are you focused on? Because if one thing is taking heat in, something else must be giving off that heat because we know energy can't be created or destroyed, it just flows. So in your lab today, when you're thinking about, okay, is energy going in or out, the thing you want to be focused on is the test tube. When we do all of our reactions in the test tube. Okay, don't focus on the thermometer. The thermometer is going to give you data, but think about the test tube itself. Where's the heat going in relation to the test tube? Okay, and I can help us out as we get stuck. Okay, all right, in our lab today, safety-wise, we do need to wear lab goggles today because we will be working with some different acids, and those are very painful and dangerous if they get into your eyeballs, so we don't want to do that. So we do need to wear lab goggles today. You can wear an apron if you want. The only thing that would cause damage to your clothing, once again, are the acids. They can corrode, and you would find a hole in them later on. It doesn't happen immediately, so if you're worried about that, you can wear an apron today. If anything by chance spills today, I need you to let me know before you clean it up. Because depending on what it is, we might need to neutralize it before we just start wiping it up. Okay, so if anything spills, just be like, I made a mess, come help me. Okay, and we'll get it taken care of. Okay, you're going to be doing 6 different reactions with the goal of identifying it's an endothermic reaction or it's an exothermic reaction. And then in the conclusion part, you'll be talking about bonds breaking minus compared to the bonds forming. Okay, two of the reactions I'm going to do as a demonstration, and I think at the start or the end. We'll do them at the end. So we'll have you start on the ones that you're just doing in the lab. Which you don't even have your lab papers yet. Let me give you these. Because last time we only had our other paper. So if you flip to the very first page, you'll see the lab sheet there. So in the lab, you're going to work with the person you're sharing the table with, but you'll be at a station as a group of 4. So you can still talk to each other about it, but you should be doing 2 different, not different, but your own reactions so you can be more hands-on, right? Oh, did I miss anybody? I just talked to you and then I left. Goodness. Okay, turn to the first page here. So as always, in the lab, there's an instruction sheet that tells you exactly what to do. Okay? As we learned, hopefully during the silver lab, you should read the instructions before you do anything. Then, if you have a question, you can ask me to clarify one of the steps. But if you come ask for my help, the first thing I'm going to ask is, well, what did the paper say to do? Okay, so read that first. If you're still confused, please ask. I want to help out. So on your data sheet here, number 1 and number 2 are going to be our demos. So if you want to put a little arrow next to 3, that's where you'll start. Okay, so you're going to start on number 3. And then we'll do number 1 and 2 at the end. Okay, and then up here at the top, it shows you the reaction that corresponds to it, which will help later on when you're answering the questions. Okay, all right, any questions for now? Okay, bring your pencil, and let's go make some things together.